I guess we're getting slightly organized, so I'm just keeping all the pens in place for myself. Okay. Yeah. Okay. All the color requested, click on video wall to use the presenter right in full screen mode. Okay. Yeah. Thank you. Okay, so I want to show you something in today's class. It's no, I'm also trying to give you some ideas on what possibly you can work on. We were talking last time about using this. Okay, so before I actually use the whiteboard, I think now I'm actually going to show you something and make you think a little bit about how this cloud is changing. How cloud, what are the issues with using the cloud for developing applications. I think that's very important. Okay. Um, One of the interesting projects the students could think of taking is how do you migrate and what are the challenges of migrating current applications to cloud. You can develop a small application locally and then try migrating it to the cloud and see what are all the issues that come up in migrating the applications to the cloud. That's a very interesting project. Okay. Um, I'll write somewhere, if somebody is actually collecting all these thoughts, one of the things that you can do is you can write these possible projects, the student projects that they can take, and also in the process also can think of, what are the research problems one can think of, and what is the, suddenly a good student project. One of the ways the faculty also should work is when you start at the undergraduate level, when you have a small project, you should scope it such that they can think of a very small issue and can work on. At the MTech level, you can expand this further and then sort of take it a little more deeper. At the third level, at the research scholar level, you can try to expand this problem and give it for much deeper study. That way you can integrate your work, teaching plus research plus student projects together into some logistic, holistic point of view, and that can create really good teams working on a breadth of the problems and also depth of the problems. That is important for colleges to develop in the long run. For example, if you just look at this migration, of applications from local system to the cloud system, you can think of variety of sub problems in this. For example, one is from a cost perspective. Now, what is costed in the local area network is different from what is costed in the cloud. To make this clear for you, I'll just show you, for example, a simple application. Not simple; it's a sufficiently complex application that we've been attempting to develop. As I said, we're incubating a startup company in the Silicon Valley called the Twitter Play, and this actually was runs both in my local area network as well as in the cloud. That's Azure cloud. Okay, I'll show you this and then discuss with you what are the issues when it runs in a local cloud versus what happens if it runs in the Microsoft Azure cloud. And also in the process discuss with you how to migrate applications to the cloud. Okay, that's I think is interesting from variety of reasons. Okay, now let us look at this issue here. I probably have to share my desktop at this point. Okay, say okay, so I'm just no sharing my desktop. I'll actually go to this okay local area network. No 10 dot. Yeah, this I think you can see the Twitter Play. This is something that we've been working with this company in the US called Quantum Ventura. This is a Silicon Valley startup company. This whatever has been developed actually works in the local system, as you can see 10.6. So it actually logs me into the Twitter account and then actually comes back and then starts a variety of technologies have been used here, including the Node.js, which is becoming very popular in terms of developing the applications for the Twitter, as you can see for web applications. Now here you can, for example, you can give, you can track some custom keywords. Okay. Um, okay, so you can just go here and then give, for example, Hillary Clinton. Okay, you want to track whatever tweets that are coming with Hillary Clinton. Okay, so this is supposed to be tracking. As you can, this will give you the word cloud here, all the keywords associated with Hillary Clinton. There is a keyword cloud here, and then there is also a hashtag cloud that will come here. It will also start showing, for example, who are the most influential people. As you can see, most influential people who are actually associated with these tweets. Okay, slowly it will build the hash cloud and all that. It will also show the locations of the tweets from where these are coming in. So as this starts building up, as you can see, this is work in progress. As we start, showing all this is for this can be employed for a variety of things. There's lots of technologies that are being used, no, underneath this one application itself. As you can see, the hashtag will start coming. So I think this is one of the most influential hashtags. I think this is associated with Hillary Clinton, as you can see, and then so you can start analyzing. This is an application that was developed, okay, in the local cloud. Okay, this is part of the local cloud one here. So I will actually try to go off to the okay. So let me also show you the same application was developed in the Azure cloud, Microsoft Azure. This was deployed in the Microsoft Azure cloud. So I think if you actually go to twitterplay.1, twitterplay1. Sure, I thought I had this already stored, but I don't know. Okay. Twitterplay1. AzureWebsites.com. Just one second. Let me just get the Nicole. Nicole, where is the Twitter Play? This thing, the website, Twitter Play 1. Azure website. Okay, I think it is Azure website. This is actually deployed in the Azure websites.net. Okay, the same one actually runs from the cloud as well. Okay, now if you actually do this, actually testing this in the cloud is a much bigger problem, because a lot of things we don't have control. For example, this is running under the IaaS server, and then a lot of things that happen there, and then the behavior of the Twitter Play in the cloud is so much different from see, now you can see I have an error coming up here. Okay, so for me to actually track this error, or see where this error is coming from, as you can see, this is actually the IaaS node. Okay, there is a there is a internet server hosted by Microsoft Azure. So you go inside there and then use the Node.js and then deploy all the scripts there and make this application run there. When an error, something like this comes, debugging is an issue in the cloud. Okay, how do I debug this? As you can see, it's working perfectly well in my local server. When I just migrated this, there are some issues. Sometimes it works. It's still not stable. This is one problem. For example, what tools and techniques that you will provide for people when they're migrating their applications from the local area network to the cloud? This is one very interesting project that people can think of. Okay. The other thing that you can think of here is, for example, in the local area network, this application, how much data is transferred. As you can see, I'm actually pulling a lot of data, okay, from the Twitter. Okay, storing it somewhere, and providing all these interfaces for that. Okay. Now the data transfer rates in my local area network is not charged at all. For example, it's zero charge. The data transfer rates, I pay zero charges. But now the minute I deploy this in the cloud, the instances could be at multiple places. For example, in this particular case, there is a front end, and then it actually stores into MongoDB all the tweets into the backend MongoDB, and then I do variety of things. All of this could be running on multiple nodes in the cloud. Okay. Now, when I transfer the data from one node to the other node, the charges could be completely different. The way the cloud charges me is for data in rates are free, data out rates are charged, which means that when I pull out a data from the node, I'm charged. For example, in this Twitter Play case, there could be several GBs of data that gets pulled out because there are lots of Twitter feeds, and then I'm actually working with the Twitter feed. My casting, the architecture cost in the cloud could be completely different from my architecture cost in the local area network. Okay. Uh, Testing problem. How do you test the application when it migrates from the local network to the cloud is one problem. For example, in this particular case, I'm migrating the application from the local area network to the cloud. Okay. From my local area network to Microsoft Azure on the internet server with Node.js installed there and doing all the same application. What we're seeing running on my local area network, I'm just trying to run that on the on the website. There are quite a few problems. That's one part. The testing is one part of it. What kind of techniques and what kind of help that should come in when applications migrate to the cloud? What kind of tools that should be available for testing things? Okay. The second more important issue is these are BTech level, small BTech level projects that one can think of. Okay. We can also further think of, for example, the architectural cost. In fact, one student from SSN has done this for me here. She wrote a nice report, giving at the end what is the architecture cost of actually having it in the local area network versus in the cloud. Okay. Again, if you have different cloud providers like Amazon versus Microsoft Azure versus blah blah, DigitalOcean or Rackspace, the cost again could be different. For example, they could be charging some cost for the data in or data out, or they could be actually provisioning let us say one node is provisioned in one region, another node is provisioned in another region. Then the data transfers are much more costlier than actually locating them in the same rack. Okay. All your server instances, if you load them all at one place, then that's another aspect of how do you architect. Okay. So small architectural issues. For example, the auto scaling issue. If the load on this whole server increases, do I auto scale? How do I auto scale the backend infrastructure? Okay. If I use a particular this thing, what kind of auto scaling properties do I get? All these are interesting small BTech projects. Okay. From this you can think of a research project, a good research project. You can think of a really good research project by saying that you will look at for example design patterns for architecting applications in the cloud. That could be a very good research problem. Okay. How the current design patterns or the new design patterns one would like to think of, if our architectural patterns or design patterns that will be applicable when you are thinking of cloud computing. That could be an interesting research problem. So when people are picking research problems, and especially the teachers or other people who are involved in doing research, should think of having first all problems done at the BTech level as undergraduate projects. Then you can think of master's level projects, and then you can think of research problems, and you can start looking at how the same problem can be used as a okay, as a research problem. That's important for people to think of in that direction. Okay, a variety of things here in this space. You can think of some of the research work that we have done. I'm going to expose you, slowly, but then that will take some time for us as part of these lectures. Okay. But suddenly the variety of issues, okay, variety of issues of working with, and you can think of some small student projects as I'm giving them, somebody can collate them and sort of share with the community, their community of students who are actually participating in this, and see if no, they will be able to do it. Some help can also come in as part of our this thing, but it's interesting to work in that particular direction. Okay. With this, I think I sort of trying to now get on to how the abstractions are important, how we will start looking at my desktop sharing at this point of time. Okay, um, okay, and I'll probably use for a small period my blackboard. Okay, my whiteboard. Actually, this is a whiteboard, not a blackboard. Okay, I will try to use the whiteboard to give some idea on exactly what we will do in the MapReduce case, how the programming abstractions are very important while programming on the distributed systems. Okay, right? This is becoming very important. For example, I showed you a way of programming. Okay, in fact, hands-on, I actually went and developed a small client-server Java program, showed you how multi-threaded programs can be developed and all that. Now imagine if you have to develop a distributed program that needs to run on, let us say, 100 or 200 nodes or 1000 nodes. Okay, if you write programs the way I've taught you, how you wrote your first client server program, um, do you think you're likely to have problems? Okay, let me ask this question and see how many people think that there is a practical way of developing. Okay, no, what I have done for one node, one server and one client, I have actually shown you how to write the program. Okay, uh, let's just write the Java sockets and then open the Java socket connections and then send the message and then uh, try to connect up the server with the client, send the messages, and the server will respond with the message. If possible, you can increase it to multi-threaded program to make it faster. Okay, how many of you think that I can use the same method for writing programs? Okay, now I want to write a Java program that runs on 100 nodes. Okay, what is the immediate problem that I will get into? For example, now a single program on my client side has to work with 100 machines. Okay, 100 machine servers are there on the other side. I want my client to actually work with 100 machines on the several segments of the program running on 100 servers. Okay, if I need to write this program, what kind of problem will I get into? Can somebody answer me? I'm looking at the chat. You can just put it into the chat box. I want to see if there's a response that comes in from the chat box from me. Okay. That also tells me that people are able to scheduling those requests. Okay, that's more than scheduling the requests. Okay, they may be because once the server receives this request, probably the thread will pull it and do. Some other college is saying synchronization. So what kind of synchronization problems I'll get into? That's a good answer. Now, what is the kind of synchronization problems I'll get into? Traffic. Kakinada is saying traffic. Okay. What will be the traffic issues? Imagine, you're just writing. Now you have to put yourself. You're just writing the same kind of Java program for hundreds. Okay. What is the first problem that you will encounter? Of course, synchronization is a very good answer. Even before you can get into synchronization, you can make this program trivially synchronous so that all that the client does is it sends distribution and integration. Let me put this way. What my client does is it just opens a socket to the server side. What I did, the same thing. It just sends a no, for example, saying Janikiram, and then the server is saying I said Janikiram. That's all. Okay, server client said. But then instead of sending it to one server now, I'll send this request. Same. The client opens another socket to another server, sends again the message which gets printed by that server. So I want to do this for 100. I want to do this for 1000. Okay. Do you understand now the problem? What is the first problem I'll get into while writing uh, this program? Simple problem that I'll get into. Okay. 1000, 100 nodes, 1000 nodes, 10,000 nodes. Imagine, put yourself in that mode. Okay, all that I'm doing is a very simple. There's no synchronization problem involved in here. Client just opens the socket, sends the whatever data it has. Server says client send this. That's all. Okay, but I want to do it for 100 nodes, 1000 nodes, 10,000 nodes. Can I write the same way I wrote my Java program? Will I be able to do that? Problem that I will get into. Simple server can't handle that many requests. No, see, basically here they're all independent servers. No. Okay. Okay, they're all independent servers. So server will handle only one request. Client will keep sending it. Okay, one client will send now 1000 requests, 10,000 requests. Okay, so server is still simple. Okay, the biggest problem, connect to new server. Okay, what is the problem in that? Connect to new server. Okay, what is the problem in connecting to new server? You imagine you have already written this program. I actually shown you how you write this program. Okay. The biggest problem here is, imagine now there are 1000 nodes. Should I tell the answer or anybody will attempt? Correct. I think Jntuk. Can you now identify yourself? Who is the person who is giving me this answer from Jntuk? You get a chocolate. Vishnu. Okay. So you have a chocolate from my side. Take a chocolate. Okay. That's an excellent answer. See, the IP address, just simply the problem is for me to now give 1000 IPs or 10,000 IPs. Just simply not manageable. I'm actually typing the IP address there and then saying which port number it is connecting to. Now my client program has to type in 10,000 IPs. Okay, which server IP address we have to give. This IPs will become a problem. See, you can no longer start programming. If the client is just doing the same work with these 10,000 nodes, I need an abstraction. I just no longer will be able to write my program saying that I will start doing the wire protocol. Okay, is that very clear for you now? Why we can't program the same way we program now using a Java on single node? If you just up to 10 nodes, maybe 15 nodes, I can manage. I can still work. The minute this number becomes 100,000, 10,000, the way I'm programming will not work anymore. So I need some level of abstraction. All that I'll say is, now give me some 10,000 nodes and just do this work with those 10,000 nodes for me. That's how I program. Rest of it somebody should do for me. Rest of all the other work should be done by somebody else. This is what we mean by an abstraction. So how our program should look like now in the cloud, as we start scaling, as we start getting more and more nodes to work on, uh, working with them at the physical level of connecting, drawing the ports will no longer make sense. And that becomes extremely difficult. If you have 10,000 nodes and you want to write a program that runs on 10,000 nodes, the way I have done it with the client server programming, that won't really scale up. And that's a key issue that we are going to now focus on. How do I program a large number of nodes? And this is the problem that Google has first encountered. How Google encountered this problem? He was going and crawling all the web pages on the net. It is actually getting all the web pages from the network, okay, in the web. Okay, all these pages are brought. The crawler goes and then picks these web pages and brings to one central location. Okay, this could be a few billion pages. Maybe it has started with few million pages. Now it's few billion pages. Okay. Now what is the work they wanted to do? They look at these pages look at the keywords in these pages and index them and do some processing so that they arrive at a page rank of all these pages. So when you search for a keyword, what is Google providing? Now when you search with a keyword, it shows the relevant pages for you. So they're indexing so that the top 10 pages, okay, top 10 relevant pages for that keyword they're showing you. So that is the processing that they're doing. They're just looking at each page. Like, I give you, okay, one book, okay, War and Peace by Leo Tolstoy. It's a really thick book, okay. Probably the best novel of all times is War and Peace, okay. Once Somerset Maugham actually was asked to rate the top 10 novels of all time, he put War and Peace first, War and Peace second, War and Peace three. First three ranks he has given to War and Peace, and after that only he rated other novels, okay. So if you take this War and Peace, it's a very thick book, okay. Now one of the things that I ask you to do is I'll give you this War and Peace novel, and then ask you to count how many times the characters have actually appeared in the pages. For example, Antony is one of the characters. I think there's no hero as far as I've read it. There are about 90 characters, and this panoramic of what really happened during that period of time. The social this thing, unlike our current novels where the hero is does everything and is super person. The heroes generally are normal people. Okay, in our real life, there's no hero. Everybody is an ordinary human being, right? So now Antony is one character. Okay, now this one character, you want to find out there are different such characters in the novel. So I'll give you the problem of counting the number of times this word appeared in the novel, War and Peace novel. Then what will you do? You'll keep on going in every page, and then maybe at the end of every page you'll put some count and then start counting. Okay. One way is just run through the entire set of pages and then count it. Okay. If I give it to one person to do it, he's obviously going to. First problem is, as we are telling in the last class, this is what we meaning by big data. Okay, as the size of this book is increasing, expanding. Okay, now I'll give you a 10,000 page book. Okay, suddenly one person can't even carry it. Okay, the load of this book is, let us say, some 30 kgs book is what I'll give you. Then you can't just carry this 30-page book yourself. So your capacity is to carry only a small book. Okay, so you can no longer carry. First thing is, let alone count. You can't even carry this book. Okay, so suddenly it's beyond one person to be counting these things. Okay, now you're going to put multiple people. Let us say you put 100 people to do this job. Then how are you going to do now? You're going to now think of splitting this book into some 1 to 100 pages first, guys. 101 page to whatever number that you split this book into, you will split it and give it to each person. Now what does each person do? Each person goes through this and then does something, and then okay, the same task is done by them, and then finally you need somebody who takes all the counts of all these people, finally does the collating, and then gives you the final answer. Okay, this is what we slowly moving into what we mean by big data processing or big data analytics. Okay, this is big data. Now, if I give you just a small book of 100 pages, it is easy for one person to do it. As the data is becoming bigger and bigger and massive, now this web data is becoming. So Google is trying to now index these pages. Suddenly, one machine won't be able to do it. That's where they started creating these large commodity hardware. With the commodity hardware, they used to buy some commodity hardware, 10,000 of them, and then create this data center. Okay, 10,000 server form. Okay, now if you want people to write a program for this word count, okay, typical program like this word count program, you need to write this word count program that runs on 10,000 nodes. You no longer would be able to write it in the client server program the way I wrote my Java client server program. It's just simply not possible. Okay, there are 10,000 servers, and then some servers may be down at a given point of time. You've assumed that your program always is going to send a socket connection there, and then the socket connection doesn't get opened up, an exception will get generated, and your client will abruptly terminate because there's an exception of, so you never know which of these 10,000 machines could be down at any given point of time. You won't have control. So all traditional ways of programming on these 10,000 nodes will fail. Okay, that is what we are actually reaching now. Okay, what we are saying is this is now no longer possible for us to be programming in the way we have programmed previously. And that's where this abstraction of MapReduce and Hadoop comes into picture. Okay, this is where people have discovered a new way of programming, okay, on these machines. Surprisingly, in today's class also at IIT Madras, I was telling them, okay, I had a student, first PhD student called Professor R.K. Joshi. He is now a professor at IIT Bombay. We were doing some work in 1993. We were doing a work called, for actually having parallel load distributed on some 18 Sun workstations and 3 IBM RS 6000 workstations. We were having in the department some 18 workstations, Sun 3 bar, okay. I'll just show you this because the problems are very, very similar. In fact, what we have developed that time looks surprisingly so similar to what is the problems that we are solving now. Okay. For example, what we've been solving as a problem is the following. Okay. And I also refer you to the papers. From now onwards, I give you the textbook plus the research material that we've been working on for a while. So if you basically look at it, they are actually Sun, okay, Sun 3 bar 50, 15 of them. Okay, these are connected. This is 1993. Remember, this work is 1993. This work is when it is actually done. Okay, these are 18 of them, 18 nodes. Okay, and then we actually have IBM machine, IBM RS 6000 machines. Take 4 of them. Okay. Now, what we've been doing is we are trying to parallel program on this machine, on this cluster, entire cluster. Okay. This cluster is connected with a high-speed LAN. The high-speed LAN that time is 10 Mbps. Okay. And this also has a 10 Mbps network. And these two are actually connected by a smaller link, so kbps link. Okay, this is the configuration that we had. We were trying to do parallel programming on top of this. Okay, so given a problem, given a program, the program will split itself on all these machines and run on all these machines. The whole idea is yeah, the whole idea here is just bringing it closer so that the this thing is visible. So if you look at, there are actually 18 Sun 3 bar 50 nodes and 4 IBM RS 6000 nodes. These are about 100 times faster than these machines. Okay, Sun 3 bar 50 machines. So given the same program, we were trying to actually program on these machines, and one of the abstractions that we developed is called the parset, okay, parallel data set. Okay, this is something that we developed in 1993. Remember, okay, the idea of this parset is given a function and given a data D, this function can operate parallelly on all these data. Okay, so this data is declared as a parset. So given it now, in this case, the data is your is your War and Peace novel. Okay, the data. Okay, large data. The function is the word count. Okay, the function is the word count, and the data is the is your novel. Now what do? The word count will now start working on the split data. For example, if this data is split as D1 plus D2 plus D3, this function will operate now on this and then will produce FD1 plus FD2 plus FD3. Okay, so you can split this data since it's a data parallel. This function, par function, can operate on all of them independently. Okay, this can operate completely independently, and this is what we have actually developed as. This paper was published in as parset paper. I will share this paper with all of you. This is a paper that was is part of the grid computing book. If you actually have my grid computing book, that gives you this paper. Okay, the initial version of this paper that was published is part of this. Now, surprisingly, after 20 years, Google was trying to do the same thing, and then this gets modified in this thing as a MapReduce program. This function F is called map, and when you are actually doing this, combining the results of all of this comes as a reduce function as far as Google is concerned. So this is the map function. You write a map function and you write a reduce function to actually combine the output of all the map functions. For example, in the case of the book example that I was giving, the War and Peace book, large book that we are talking, and then we are splitting that book into multiple sections, D1, D2, D3. The word count program will try to find out the number of times the character occurred in the first split, number of times this actually occurred in the second split, number of times this has occurred in the third split. Okay. Now, what you want to do is combine the individual values and then produce a final output saying that how many times that has happened. It becomes a simple exercise of adding up all the numbers that I have with these sections, so that it could be more complex than that, but that becomes the reduce function, which combines the output of all of this together, becomes the reduce function. So I'll specify a map function and a reduce function, which surprisingly is the same kind of stuff we have been doing in 93, which is a parset, which we called it as parset. Okay, and this is the model that we have been doing in 1993, and then that was published as a paper. It's a published paper. In fact, you can read the paper. There's nothing, but the same thing actually comes in. There is actually little differences because the data is not stored for us in a file system, distributed file system, whereas the MapReduce will look at this as a file system problem. An external file system is required as a Hadoop file system. So I think what we are trying to now tell you is, if one single node is not able to handle, you no longer will be able to write your programs on large number of nodes the way you traditionally wrote. You need to raise your abstractions. Okay, how to raise these abstractions? This is the most important discussion that we will get into. We no longer will write these programs in the traditional way, and we will write, for example, one part that we are going to look at as part of this is what we call as a MapReduce programming. Okay, MapReduce programming is the first raising of the abstraction in some sense. Of course, take parset is before that. Parset also talks about raising the abstractions. In fact, most of my students who read parset paper tells me that, sir, it looks surprisingly as a MapReduce. It is actually, okay. In some sense, problem that we have been, trying to solve in 1993 is a similar problem, and hence both these look very similar ideas. Okay. Now, what I'm going to do is I'm trying to now teach you, okay, in the next couple of classes, before I go further and then start telling how how we are going to do the MapReduce. The basic thing is the programming abstractions have to be raised, and that's where I think we will see the first paradigm of increasing this abstraction to what is called MapReduce programming. Okay, I'm going to spend some time explaining what is MapReduce and how we will use the MapReduce and how we will program in the MapReduce. For that, we will try to build a context and then actually show you practically how are you going to do MapReduce programming. Okay, right? Before I go further, this I will start in the next class. On Friday, I will start what is MapReduce abstraction and how you do the MapReduce programming, right? But in today's class, I'll spend little more time on actually trying to teach you why the abstractions are important in programming. Even in software engineering, abstractions is everything. Okay, in computer science, who is a good computer scientist? One who is able to have good abstraction skills. Not so much analytical skills, they're important, but then I think if you're choosing computer science as a profession, you want to be in computer science, one of the key requirements is you should have a good abstraction skill. Okay, what is a good abstraction skill? Able to see or raise raise your understanding of things to much higher level. Okay, for example, you know what is important versus unimportant. If you look at managing 1.2 billion plus people, okay, we are 1.2 billion, I think, okay, or 120 crore people. Okay? If everybody is talking to everybody else, okay, we don't have any abstractions. Okay, the whole thing is one country and everything is centrally managed from Delhi. Then you know what kind of problems we'll all will get into. Everybody has to go to Delhi for everything. Then it won't really is an improper abstraction because you're putting everything at the same level. Okay, that's where it is not a good abstraction. Now, if you look at India as a country, you have several abstractions. You have a local panchayat government, and then you have a mandal panchayat, and you have a district, and you have a state, and then several states put together. You have a center. So, the multiple layers of abstraction. Okay, that is what we mean by abstraction. Abstraction means creating. Okay, these layers. For example, in the case of programming, writing C programs is a higher level abstraction compared to writing it in the machine level code. Okay. Most of you may not be even familiar about machine level, writing programs at machine level. For example, 8086. You take the chip. Previously, the programming is do it in the assembly level language. Write in the assembly level language code, which is extremely difficult. If you're writing large programs, writing them in machine code is impossible. So you have a compiler. You write it in a higher level language like C or C++ or Java. Okay. Now you have risen the abstractions little higher. So people write only in the high level programming language C or C++. The compiler automatically generates the required machine level code for you. Okay, writing in machine level code is impossible for you. So you will write it in C or C++. Okay, Java took this abstraction a little higher. In fact, it took the distributed programming and said that the class files can be shipped anywhere and can be executed anywhere as long as the JVM is actually there on the operating system. Okay, it took the bytecode portability one step above so that the abstractions is further risen at a higher level. We also discussed this problem. For example, the network programming, if you're doing in Java, the socket abstraction is available for you. All the things that you're doing in Java, socket programming, is at the language level. If you're doing with C, you will actually end up either doing with on the Unix machines, on the Linux machines, you will open the sockets as per the Linux libraries that are available for that. Okay. If you are writing it for Windows machine, you will use the WinSock library. Okay, there are different operating systems. You will write it differently. You can't write network programming in C. Depends on the operating system on which you are programming. The minute you go to Java, it's a higher level abstraction. Okay, Java socket programming in Java is same irrespective of whatever operating system you are using. Whether you are using Windows or you are using Linux, the operating system is just simply the same. Okay, now the abstraction is taken, network programming abstraction is taken one layer above. Okay, now if you go and look at what we are trying to do is, even when you use Java and write the distributed programs on one node versus n number of nodes, as the n number of nodes are coming into picture, you no longer can write the Java programs. This is like not being able to write the machine level code, large amount of machine level code. You need a C and then you need a compiler. That is where, when you want to do the kind of program that I said, word count program on a large textbook, okay, on a large novel you want to do, then you're splitting this and then distributing it and then writing these functions, which are the word count functions. Okay. Now this has to be done at a very high level. That's a framework. The abstraction has to be now risen further. That's where it is risen to what is called a map reduce abstraction. Okay. You specify a map function, you specify a reduce function, there ends your job, and specify the data on which they should be operating. Rest of it is done by somebody for you. If it runs for 10 nodes, 100 nodes, 200 nodes, 10,000 nodes, automatically the program is deployed and it automatically runs. You don't need to do anything. Okay? This is very, very important, that the abstraction is risen to a higher level. Okay? The minute is risen to a higher level, your task becomes very simple. All that you will now, for writing the distributed programs, you don't open these sockets. You don't send messages, which will result in synchronization problems, whether your program is running correctly, whether the server has been started before you're opening the network connection. All these problems will disappear. So all that you will specify now is, this is what my map function is, this is what my reduce function is, this is what my data is. Rest of it should be done by the system automatically for you. So what does your distributed program writing will boil down to? It will boil down to just specifying a little bit of code. What is the map code? What does the map should do? What should the reduce should do? What is the data on which this whole thing should be running? Okay, that's how you want to now raise your abstraction further. Okay, in distributed programming, that's what we call as a map reduce paradigm. So we will start delving deep into map reduce aspects. As I am doing, I will also introduce you to the research that we do in this space. A lot of research that we do, and which will be interesting for a lot of people. So the idea is to also bring that research content for you to the extent possible as we are doing it. Okay, I think I will stop here and take few questions before I go further. Okay, next class possibly I will show you how we actually look at the map reduce thing, and slowly I'll actually take you into the cluster and then start doing the map reduce programming. There are lots of interesting stuff there. Okay, we'll see how much of it we should be able to cover. Okay, are there any questions? I can spend some 5 to 8 minutes on the questions before I log out. Okay, are there any questions? Is no is the lecture coming no okay for all of you? There's no technical problems, I guess. Okay, yeah, I think that looks all right. So if there is yeah, are there any further questions on give audio to Jntuk? Okay, you want me to start the okay,
please.
yeah, I gave the
Sir,
audio
about
to this.
the architecture you have shown. Hello, sir.
Yes, yeah, please.
Hello, sir.
Yeah, please go ahead. I'm able to hear you.
Sir, this is Professor Murthy.
Yeah, please go
Sir,
ahead.
sir, you gave the architecture, right, sir? You said you
Yeah.
have some form. About that, I just need little clarity, sir. The very
Which one?
architecture you have given. You worked out in 93, you said about that.
Correct. See, this
You
architecture
you
that
did the work preliminarily, right, sir? in
No,
93,
no, this is,
93. About that, a
yeah,
little explain.
yeah. See, this I'll also share that paper with this community. Okay, this is a published paper. This is not a preliminary work. Actually, this is a detailed work, and the final work, which is a 20-page paper, appeared in IEEE Transactions and Software Engineering. It is that is in 1999, I guess. Okay, the final paper, putting all this together, appeared in the IEEE Transactions and Software Engineering
Great.
as a 20-page paper. I will share that paper with you. See, the architecture is the following. We actually had 18 Sun bar, actually there are 15 Sun 3 bar 50s, which are diskless machines. Okay, and there are three which are actually Sun 3 bar 60s, which are actually the server machines, which have actually the
Diskless machine.
files also with them. Okay, this is in one lab called Sun Lab, and this is connected by a 10 Mbps network. Okay. Now there is another. We have a computer center where we have four IBM RS6000 workstations, which are housed in another building, and they're connected with the same 10 Mbps network. This is in 93. Okay, and then both these are interconnected by a few kbps line. The backbone in IIT Madras that time was a few kbps. Okay, in fact, if I have to log in into these machines from my house, I used to use the telephone line as a modem line. I used to log in, and then that used to give me few kbps. Okay, now we have a 1 gbps network. That's different. Okay, now in this network, what we are doing is we are doing parallel programming on these workstation clusters. Okay, that's what we are doing. Okay, the idea was to actually have a program that splits its data and then executes on all these machines. Okay, the additional challenge was these machines are being used by other people also when we are actually trying to do the parallel programming. So we have to split it as per the idle time that is available on these nodes and execute it so that everybody equally balances. Okay,
Okay, sir.
and this is a task that we were trying to do, and for that we actually designed this construct called the parset. Okay, you have a data set and it
So
can be
runs in
split
background,
according
sir.
to
Your program.
what is that? Yes,
Okay, sir.
what were you saying? Hello?
No, so your program is run in background, sir.
Yes, this
Your
parset is a
program
higher
is run
level
in background,
abstraction.
sir. Then, because the other people
Yes,
are also use. Sir,
correct.
you said
Actually
that
we are sharing.
the
Hmm,
other people are also using the machine.
correct.
It runs in
Actually,
background, sir.
yeah, everything is run in the background. So we have actually a middleware that senses the available idle time on that machine and then gives that much of load to that machine. For example, imagine there are 20 people, who are doing various other tasks, but they have little bit of a time, free time for you to be doing your work. So we sense what is the free time they have. So each person can be loaded up to 10 hours. Now each one is getting the local work itself is taking 9 hours for him. Then we say 1 hour free time is available with that guy. So we give him that much work. So we distribute depending on, we sense what is the each one's load dynamically, and we give an appropriate chunk of work for him to be doing. Okay, and finally all of them should be finishing the work at about the same time. This is the challenge that we had, and for that we designed this parset. So you can write your program saying that my parallel data set is this, my function is this, then the program will compile automatically, senses the load at the time of running your program, appropriately splits your program, runs on all these machines. Okay, that is the work that we did at that point of time, which is surprisingly the same problem that we are more or less solving in MapReduce. Okay, right?
So this requires as an input from each machine, which is the free time is one parameter unit, sir. Then
Correct.
it has
What
to
we
equally distribute
correct,
it has to equally the load among the existing machines. So
correct,
your job
correct,
has to take care of this.
correct. Okay. In fact, I can show you the interesting problem here. Additionally, the Sun machines are about no few times, about 20 to 25 times slower than the IBM machines. Okay, and on top of it, you have to sense the load and have to split your task equally among all these nodes. And one of the key results that we showed is it is possible to do this, which means that you can do parallel programming on a network of workstations. That was the key result that was
Yes, sir.
established in 1995.
One
Okay,
more challenge is
yeah,
excellent, sir. But one more challenge is the load may dynamically change at one specific
correct,
point of time.
correct. And in fact, you have to sense it. That's one of
The
the
load
problems that,
dynamically changes.
uh, yes. Then you have to sense it. After putting the load, it could further change. That's what we are actually going to show you in the MapReduce case also. If you extend this to MapReduce problem, the nodes could be
Yes, sir.
unevenly loaded. They can be heterogeneous. So we extended our model, and in fact, I'll show you the results of working on that in the MapReduce case also. Okay,
Uh,
that problem is common across all distributed systems. Okay,
that was actually pinching me, sir. Sometime. Yes, sir. That's what. Yes, sir.
yeah.
Then it's
In fact,
quite
we
interesting
show
also
you
at the
how
same
to
time.
actually one map, if
It's
it
nice,
takes
sir.
long time, a skewed map, how do you balance in the map reduce case? We did a lot of research work on that. That's what we are giving to one silicon-based company called Altiscale. Some of the work that we have done on that space, we're actually partnering and giving that work. Okay,
Yes, sir.
there are extremely interesting problems in that space. Yeah. Yes. Any other? Yeah. So, is
Yes,
that
sir.
clear?
Thank you for putting us there.
Yeah. Yeah. In fact, I will share those results with you. The idea of doing this also is
Sir,
also create
a
some
small
research.
note, sir. Friday is holiday,
Yeah.
sir. October, sir.
For this Friday is a holiday for you? Yeah, I guess for us also it's a holiday, right? Yeah. Okay. So we will not be meeting on Friday, right? We'll be meeting
Yes, sir.
on Monday, I guess.
October
Yeah.
2nd.
Okay. Yeah, October 2nd is a holiday, correct. So we
Yes, sir.
won't be.
So we'll
Yeah,
meet
sure.
again
For
on.
us also it's a holiday. Yeah. So I can spend a few more minutes with any other college if they have questions. Okay. I suddenly want them to think more deeper way, because this is an emerging technology, and then if what kind of student projects they can pick up, if there are questions on that, I'll be more than okay. Yeah, see, I can share the IEEE paper. All of you have actually got access to the IEEE digital library. I guess that's a part of So you can look at the if you have access to please look at this paper. Okay, anonymous remote computing. Okay. I think it should give you, a paper leading to IEEE transactions on software engineering. Okay, I can share the, I can share the desktop for a minute. Okay, and show you the paper. Okay, if you're able to get the desktop, please look at the desktop. I'll show you the paper. Okay, and also show you the results that I was talking about. Okay. Um, I hope I'll be able to get the uh, there are a PPT also that comes up. You can see that, okay, including the slides that come for this, as you can see here. Okay, uh, can see this. Okay. Anonymous remote computing, a paradigm for parallel programming on interconnected workstations. Okay, this is a paper that's available. As you can see, this was January February issue of 1999. IEEE transactions on software engineering. As this thing shows, parallel computing on interconnected workstations is becoming a viable and attractive proposition due to the rapid growth in the speeds of interconnection networks and processes. In case of workstation clusters, there is always a considerable amount of unused computing capacity available in the network. However, heterogeneity in the architecture and operating system, load variations on machines, okay, variations in machine availability, and failure susceptibility of networks and workstations complicate the situation for the programmer. In this context, new programming paradigm that reduce the burden involved in programming for distribution, load adaptability, heterogeneity, and fault tolerance gain importance. This paper identifies the issues involved in parallel computing on a network of workstations, and it provides this paradigm called anonymous remote computing paradigm to address the issues specific to parallel programming on workstation systems. Okay. Arc differs in the sense that you just have a single program entity that goes as remote instruction blocks and gets executed in the this is a very detailed paper. If you actually read this, this tells that what is the unused capacity and all that available. The more interesting result, which Professor Moocs is asking, comes somewhere down the line. Okay. This is available as part of the grid computing textbook that we give. As you can see here, these are the Sun Spark, Sun 3 bar 50s and Sun Spark machines. These are named at that point as Pelican, Bronto, Taranto, and Vanaville. Okay, number of users on the machine 2496 at the time you have taken. We actually quantify the unused capacity as horsepower factor. So this is the horsepower factor. Okay, depending on that we allocate the task size allocated. You give an appropriate task size depending on what is the HPF available. Okay, horsepower factor available for these machines at that point of time. You can see you almost get the same execution time on all these machines. So the splits are different. As you can see, this has got 2 into 200. This has got 18 into. In MapReduce case, this is equivalent to saying the number of records that you had given for them to process. Okay, and remember this is an extremely old work. Even before MapReduce came, this work was available. Okay, now the final one which I'll show you, this is the one which we are talking about. Now look at this. There are 4 IBM machines, IBM RS6000 workstations, and there are 2 Sun Spark workstations, 2 Sun 3 bar 60 workstations, and I think here we have used about 10 Sun 3 bar 50s. Okay. Now you can see average horsepower factor. The IBM RS6000 is 92,000, whereas this is 54. See the difference between these two machines. Okay. Now, number of this is a parallel program where we give the number of trees that each node has to process. You can see the time taken by all these nodes is surprisingly the same, almost same. We get to a point where they all almost finish at about the same time. Okay, right? The task imbalance is only at 0.15%. Okay, this is a I hope this gives you an idea. This is an interesting paper, and then you can read this paper. A lot of work that we did here. If you have the transactions thing available, then you should be able to get the this thing. Okay, is that clear? Okay. Yeah. So that possibly answers. So you can go to the website and look at that paper. I've actually shown you what what this work shows you, in terms of whatever
Yes,
model that I have actually
yes, sir.
seen. For Moocs also, that should be clear now. Okay. Yeah. Okay. So Moocs, is
Okay,
that
sir.
clear? Yeah. That should show you what we do in terms of
Sir,
sensing. Yeah. Yeah. Okay. Are there any other questions? Yeah, I think this is important for this other part is also important, knowing to get to know the work that that has been done and then how that relates to. Okay. Yes, I think then I will actually, you can look at that paper. There is a subsequent paper which is published in IEEE Transactions and Parallel and Distributed Systems called Anonymous Remote Computing and Communication. Okay, and in fact, all of this in a textbook called Grid Computing, which is published by Tata McGraw-Hill. Now the new edition is coming in. Anytime it should be released now. Then updated version of the grid computing and the cloud computing, and how it relates to cloud computing work. And no, the whole book is now ready for release actually. Okay, uh, so you can, in fact, it's much easier for you to look at them chronologically. What is the work and how the work progressed? It knits very nicely. Okay. Yeah, somebody is asking me the role of the hypervisor. The role of the hypervisor is just to make sure that the hardware is abstracted and you can get hardware as a service. Okay, that's the whole idea of VMware or any of this. But now that context is further changing. So you should be able to abstract a hardware and start your virtual box on top of it. Okay, that's where the role of a hypervisor in actually abstracting, um, right? So that's, I think, is the role of the hypervisor. Somebody is asking how to host some simple applications in the Google Cloud. It's just simply the same as hosting them in Amazon web server. Okay, uh, the name of the book is again, I'll share the desktop. You can see this book. Okay, if you just go to this book called okay. So you can see this book. I think in Amazon it actually comes up. Okay, this is the book. Okay, right. There's a Kindle version available, which you can buy from the. This has all the chronological order of the papers. Okay, so you can look at this. I hope you're getting this. So this is the book. Okay, this is actually used as a textbook in uh, very few places abroad also. In some places in Germany and uh, Pune University uses this as a textbook, and then in fact, though I sit in the board of studies of Jntuk, I myself never wanted to suggest anything to them, because there should not be any conflict of interest. But then this book has the material to some extent. What I'm relating and covering is available here. In fact, I make the cloud computing book also available. In fact, I asked the publishers to bring the ebook as soon as possible. They promised me to get it in the next 1 week. So whatever I'm covering here should be available for you. Okay, right. That's one of the material, because since I'm teaching it, I also want you to pick up the research threads, and then in fact, the big data analytics part, the cloud computing part, which has actually, I'm going to cover that. The big data analytics part is there. If you're just covering the Hadoop alone, there is a Hadoop Apache book which we can use. Okay, just for the Hadoop programming part, that I'm going to suggest for you. Okay, right? That we will